This video is going to go through the basics of section 3.9, and by now you all should be sitting with a copy of the notes that I would normally go through in a lesson with 3.9, and hopefully have looked over them and tried to get an idea of what 3.9 is all about. It is probably the easiest section in the chapter, but I know there's a big difference between reading words on a page and trying to make sense of it and actually hearing someone explain it. So even though I can't actually be in the room with you right now, the next best thing is that you get to hear my voice this way and go through just some basics, so hopefully it'll help supplement what's already in front of you. So I do have problems that are up here that are not the same as what is on your notes, because I was trying to give you other examples to help you explain a little bit more of what 3.9 is all about. 3.9 is called differential form, or just differentials, and what it's doing is it's looking at the derivatives that we already know how to find. You're not going to be learning any more derivative rules, but just writing your answer to the derivative and when actually finding the derivative in a little bit different look, a little different form. So to give you an example of what differential form is, if my original function was something like y equals x squared plus 3x minus 2, and I said, what's the derivative? You would either write y prime, or for the sake of this lesson, I'm going to write dy dx instead, equals 2x plus 3. That's the form we're used to. We write the derivative, we either write y prime, dy dx, anything like that. Differential form is a very, very, very slight change, and you're going to look at it and go, so what? Why even bother? I promise it's purposeful as we go through, but it's going to seem kind of silly when we do it. Differential form just separates your dy dx, which seems strange that you can do that, but actually takes the dy, leaves it where it is, and takes the dx and multiplies it on the other side. So differential form would be dy equals 2x plus 3 dx. And the dx goes on that side. If you want, you can put this in parentheses. It's telling you we have the derivative of y in terms of x. And again, I realize as you're sitting here, you're going, wow, that's really all I'm supposed to be doing? Why in the world would I bother doing it? I promise it actually becomes very impactful in the next chapter, and I'm actually going to show you an application here in the second part of this video as to why this would ever be helpful to us. In the meantime, just use it as a way to practice your derivative rules. You will be asked to take derivatives and write your final answer in differential form. You're still going to need to know how to do a product rule or a chain rule or a quotient rule or your trig derivatives. So if anything, just use it as a review and enjoy the ease of the derivative process. So for these three, I'll just take you through examples. The directions would say, and you'll see this in your homework as well, find the derivative and write your answer in differential form. So I know that my derivative of sine is cosine, and I know that I also have to multiply by the derivative of the angle. So I put this on purpose because I want to make sure to remind you about trig chain rules. So we get 3 cosine 3x. This is the derivative form we are used to. The only difference is that we write it as dy equals 3 cosine 3x dx. Very simple, very subtle, and you will have a question on your Chapter 3 test that is that basic. It will ask you to derive it, and it expects your answer to be written in that form. For the second one, the x squared over tangent x, hopefully you look at this and think, okay, I really need to do a quotient rule. If you really wanted to, you could rewrite that, put the tangent up top, write it as cotangent, and do a product rule. I'm going to keep it with the quotient rule for practice, but if you wanted to do a different way, you could. So we have dy dx equals bottom times the derivative of the top minus the top times the derivative of the bottom. Derivative of tangent is secant squared, all over the bottom squared. As I put it in differential form, the only real change you're going to see with what I've done so far is I really want to bring that 2x in front because I do not want anybody to confuse it as part of the angle. So I have 2x tangent x minus x squared secant squared x all over tangent squared x. And then the dx, when I write it in differential form, you have two options. You could either write it at the very end of the fraction, or you could include it as being multiplied by the numerator. I tend to just put it at the very end. It's easier to kind of plop it there. And then the third one, this is a chain rule, just a little practice. I am going to rewrite it as x cubed minus 5 to the 1/3 power. It's easier to then apply the chain rule. So I have dy dx equals power out front, power 1 less. So we drop down to the negative 2/3, and then the derivative of what's inside, which is 3x squared. I can cancel the 1/3 and the 3. I'm going to move my negative exponent down. So I'm going to do all the things that I would have done last chapter. So I have x squared over x cubed minus 5 to the 2/3. And then to put it in differential form, dy is alone on the left, and then we put dx. Again, I usually put it at the very end, kind of after the fraction. If you want to multiply by what's in the numerator, that would also be appropriate. So that's the first half of tip 3.9. So the nice thing is you already know your derivative rules. As long as you understand this one kind of change in the way we present it, you should be able to do these on your own without much guidance from me. The second half of 3.9 is actually applying differential forms. So I mentioned that we're going to use this form a lot next chapter, but we do have a quick application this chapter to show you that there actually is a little bit of purpose for what you are doing. So what I'm starting with is I'm showing you some geometric formulas. As I've mentioned before, if it's a volume formula, if it's something that you should maybe not know off the top of your head, I will present it to you. If it's an area formula, you should know it. Differential form allows us to do what's called an error analysis. Sometimes it's also called error propagation. Basically what that means is if I'm in construction or if I'm in some sort of manufacturing and I am working with objects that are squares or spheres or circles, something like that, if I am measuring my object and I am off a little bit in my measurement, let's say I have a circle, I'm producing circles for some reason, and I am off in my radius measurement by a little bit, that radius measurement being off is going to create even more error in my area measurement. We call it propagated error, or essentially you make a little bit of mistake saying, oh, I'm off by a ½ inch, no big deal. But when I really look at what that does to what I believe the area is, or if it's a sphere, what I believe the volume is, I've actually created a pretty big window for how off I could be on those answers. And that's what differential form does for us. So the first thing I want to do before I actually do the example that's down here is I want to show you what the derivatives of all of these will look like in differential form. So when I take the derivatives in differential form, instead of writing dA over dr, because that's what this is the derivative of a in terms of r, I'm just going to write dA on this side, take my derivative as normal, power out front, 2 pi r, and then I'm going to put the dr on this side. So separating those two pieces of the derivative. And the two pieces actually have a meaning this time. dA is going to be referred to as the change in area, so I'll use a delta, or the error in area. dr we can think of as delta r, and it's the error in my radius measurement. Now you might look at this and say, that kind of reminds me a little bit about related rates. It is similar. The difference is now we're not everything in with respect to time. We are just looking at how the errors in each measurement affect each other. So if I take the derivative of a equals s squared, so this would be area of a square, I would write dA equals 2s ds. If you prefer to write deltas instead, like thinking a change in, a mismeasurement basically, that is fine. The next one, volume of a sphere, I think one of the very first examples in class or in the worksheet, the note sheet you have in front of you talks about the volume of a sphere. It says that we're measuring a ball bearing, something you would have maybe in a car or different objects. If you're off by a little bit in your radius, then you're really going to be off on your volume. The way you determine how those relate is we say dV equals power out front, power 1 less. I get 4 pi r squared dr. If I know how off my radius is, that's my dr, my delta r, it will tell me how off potentially my volume will be. And then the last one, if I take the derivative of this in differential form, it would be dV equals 3x squared dx. Again, each d piece we think of as the change in or the error that has been created by human error, by the measurement error. So let me show you actually how we go through and talk about the different terminology that you'll see when you're either doing your homework or on test question. We are working with a circle, and we're talking about its radius and what error we could possibly create in the area. So the first thing you want to do is write down your geometric formula. Area equals pi r squared. Take the derivative in differential form, so dA equals 2 pi r dr. Look at what you're given. They tell you that we believe the radius is 4 inches, so that is your r, but we could be off by as much as 0.05 inches. That is your dr. That is how much you could have a change in your radius. So we have 2 times pi, excuse me, times 4 times 0.05. These problems are definitely calculator-based type problems, but a lot of the real-life ones are. So we're going to have 2 times 4 times 0.05. I'm also going to multiply pi in. I am going to use the pi button. Usually don't. Well, you know what? I'm not going to. I'm going to leave the pi. I'm going to leave it as 0.4 pi. What that means is my area could be off as much as 0.4 times pi, which if you're curious what that is, it's off by as much as 1.2566. So I'm going to write that next to it. So that means what I think the area is, I could be off by as much as a little over 1.2 square inches. Now, with these error problems, you might look at it and go, well, is that good if I'm off by that? Is that bad? And what we do, it's similar to like a science class. Well, it's relative to what you're actually measuring. If I'm off by a half an inch and I'm working with something that's only 5 inches in radius, that's a lot. If I'm off by a half inch, but I'm looking at something that is hundreds of inches wide, that's a very small error. So we come up with things that are called relative error and percent error to give a kind of an idea of how off are we. You do this a lot in science classes when you're doing labs, and you get to the end and say, okay, well, this is what I had. This is how off I am. Was it good? Was it bad? What is that error? The way you do that is you take how much you're off by and divide it by what you believe the actual area is if your measurement would have been perfect. So if my measurement would have been perfect, it would have been pi times 4 squared. I'm off by 0.4 pi. So if I take how much I'm off by divided by what the area would be if I was perfect, I get what's referred to as a relative error. It'll tell me basically how good did I do. Now, the pi's will cancel, which is why a lot of times it's easier just to leave it in the pi notation, but the decimal's fine. So I have 0.4 divided by 4 squared. I get 0.025. That's referred to as relative error. How good is it compared to what would be perfect? If you're still looking at that and going, well, is that good? That's a pretty small number. The way we a lot of times see it written is we write it as a percent, and we refer to that as percent error. Percent error is nothing more than just taking your decimal and writing it as a percent. So you'd say, well, in this problem, my error is I could be off by up to 2.5%. Not bad. Obviously, depends on what you're working with. Sometimes they have constraints where you don't want your error to be over a certain thing. But that's what differential form does for us. It uses the derivative in a differential form where each derivative piece represents the error. What if you're off? What if you just measure not quite right based on human error or machine error? How is that going to impact my other measurements? And that's what differential form does for us. Not very difficult. Usually you're working a lot with just basic area and volume formulas. The only time that you will have some problems that are a little more complicated, and I know there's one on your note sheet, is when you are working with something that needs to do a product rule. Like if you're looking at area of a triangle, when you derive that, you have to do a product rule. So you actually have some dBs and some dHs in there that you'll have to look at. Other than that, it's a lot of just plugging in and then seeing, okay, here's my error. Is it good or bad? Well, let's compare it to if I was perfect and write it as a percent, because a lot of times percent error makes a lot more sense to people to say I was off by 5% or I was off by 1%. And that is what will be done here. So hopefully that helps when you're looking at the notes. I didn't want to give you a note sheet and then no other chance to actually hear me talk about it. I will recap, and if there's any questions in class, I will definitely do that. This is the end of the chapter, so we finished with a pretty easy section after some of the more complicated sections over the last week or so. So hopefully that helps, and if you have any other questions, I will definitely answer them tomorrow.